Okay, so let's say make it more complicated. So for instance, let's say there are 60 students who study history. Okay, and then the number of students that study both calculus and discrete math, let's say there are 23. The number of students that studied discrete math and just these two, let's say there are 10. The number of students that study whatever, this calculus and history together, let's say there are 12. Is that okay? And the number of students that study all of them, let's say there are, how many? Let's say there are 5. Okay, let's say. Okay, and in that case, how many students are there in total? Now, this will be a more complicated example, but we can still use this idea. So we can draw a diagram like this. Let's draw a diagram. So there are 50 students here who is studying calculus. Is that okay? And then there are 75 here that is studying discrete math. And there are 60 students that are studying history. Is that okay? And then what do we know? We know that, we know what? We know, so 23 students are studying these two things, but then 5 of them are studying all. So let me calculate. So 5 of them are studying all. Is that okay? Let me write down. So this is calculus. This is calculus. Calculus. And then this is history. And then this is the discrete math. Okay, so let me clarify again. So I was making a wrong claim. So this 23 person, they are studying these two, but they may still study history. Okay. So if I know that this is 23, then what do I know? So this is the part, this represents the part of students that study calculus and discrete math. Am I correct? And then there are 23 of them. So 5 are studying all. So I know that this is 18. Am I correct? So this is 18. And then here, 5 is studying all, and this represents students that are studying calculus and history together. Altogether, there are 12 of them, so we know that there are 7 here. Is that okay? And then similarly, there is 5 here, and then this region. This region is history with discrete math. History with discrete math, so there are 10. So I know that there are going to be 5 here. Is that okay? Is that okay? And then what do we know? Okay, so how many students are calculus? 50 of them. So among these 50 students, 18 is here, 5 is here, 7 is here. So I will get 20 here. Am I correct? Is that okay? And then for this one, 75 altogether, and then this is 28. So 75, 28, so you get 47, right? So it is 47. Is that okay? And finally, this one, there are 60 of them in history, so but 17 of them is counted here already. So you get 43. Is that okay? Good. How many students are there? So the number of students is 20 plus 47 plus 43 plus 18 plus 7 plus 5 plus 5. So this is the answer. So let's calculate this quickly. So how many? So this is 90, 110, 128, 110, 128, 135, 145. Okay? Okay, so this is one way of calculating this. But the principle of inclusion and exclusion has a magic formula. Okay, so let's do this again. But using the formula that we'll talk about later. So there are 50 here. Okay? There are 75 here, and there are 60 here. So let's include everything. Include. So we include everything is 50 plus 75 plus 60. Okay? Okay? So we are including everything. But then, if we include everything, so we will find that this part, and this part, and this part, they will be double counted. Okay, so we exclude all this part. Exclude. We exclude. So we exclude is minus. So we exclude, include, and then exclude. So how many we exclude? We are excluding 23, we are excluding 10, and then we are excluding 12. So we are excluding this. But by the time that we exclude this part, we exclude this part, and we exclude this part, then this part will be over deducted. Okay, so we have to include back. And then how many times we should include back? Magically, only one time. So we add 5. Okay, so at the beginning, we include everything. And then we exclude every pair. And then we include every, it's not called pair, then let's call it triplet. And then include every triplet, and then exclude every quadruplet or whatever, okay? So this is the formula, and let's check whether this is equal to the same value. So this is 185 minus what? Minus 35, 45, is it okay? And then plus 5. And then after doing this, these two you get 140, 145, and you get the same answer. Is that okay? And this is the so-called principle of inclusion and exclusion. So you can do this again and again. Okay, and then let's do an example. Okay, so let's look at this. Among all the numbers, integers, from 1 to 100. Okay, how many of them is not divisible by 2 or 3 or both? How many numbers are not divisible by this number? Okay. So how do we know? Okay. So instead of computing this, let's compute the other one. Maybe this one is easier. How many of them are divisible? Maybe this one is easier. By 2 or 3 or both. If we know the answer for B part, then 100 minus the answer of B will give you the answer of A. Am I correct? Is that okay? So we are looking at divisible by 2 or 3 or both. And this one is not divisible by 2 or 3 or both. So one is the negation of the other, right? If you know the answer of this one, then you know the answer of this one. Okay? Is that okay? Okay, so among 100 numbers, so what do we know? How many of them are divisible by 2? First of all, how many are divisible by 2? How many? 50. 50, very good. So there are 50 of them divisible by 2. Is that okay? How many of them are divisible by 3? 33. Okay, so there are 33 of them. How many are there divisible by both? 16. Very good. How do you get 16 that quick? Yeah, because if you can it is divisible by 2 or 3, then it must be exactly divisible by 6. Is that okay? If and only if. So there are 16 of them. Is that okay? So how many of them here in total? So it is 50 plus 33 minus 16. Is that okay? So you add 2 and then minus the middle. So it is equal to what? 67. So this one is 67. Is that okay? Is that okay? And then this one easy. So this one is 33. That's it. Okay? So this is an example. And in your assignment, we are going to ask you more difficult. So how many numbers between 1 to 100 that are not divisible by 2 or 3 or 5? Okay, then you want to calculate what is this number. Okay? And then if I want to find out how many prime numbers are there between 1 to 100, how do I get? So I just need to find out how many numbers are not divisible by 2 or 3 or 5 or 7 that will be enough. All this number does not have any factor from 2, 3, 5, 7. So it is either 1, the number 1, or the prime numbers less than 100. So you can use this method to find out the number of primes less than or equal to 100. And this is the famous what? This is the famous method for finding prime numbers used by the ancient Greek. So it is called Eratosthenes method, whatever. Okay, so this is like you have something like this. So you have a number 1 to 100. You pass through this one, and then you filter out the primes. Okay. By the way, in this method, this is a name. There is a name for this. This is called the Venn diagram. So Venn diagram is used by the mathematician Venn, and then it is very helpful to figure out how many things are here, how many things are there, and then the relationship between this one and this one and this one and whatever. Okay, so this is called the Venn diagram. Okay, one more concept before we finish this discussion today. Let me use this one. There is always a useful method to help us to do counting. It is called the tree diagram. So first of all, what is a tree? So a tree is a special type of graph that has a node here. I call it a root. And then for each of these nodes, there can be arrow pointing downward. Okay, so here, this may be another node or another vertex here. This may be another node. This may be another node. And this may be another node. Is that okay? So why do we call it a tree? How does it look like a tree? And why is it a root? So if you look at this diagram upside down, it looks like a tree. That's it. So it is like there is a root. You have some branch here. Something like this. Is it okay? So you have a root here. And then there is some children here. The root here, it's not exactly the same as this one, but if you imagine, okay, so it looks like this, okay? So you can have, so for this node, you can have this one, you can have this one, you can have this one. For this one, you can have this one has this one, and this one, and this one. Is that okay? So that's why we call it a tree. So there's a special name. So, okay, so there's a special name for this one. Each node have arrows pointing downward, right? Okay, for this node x, these two are called its children or child. And the one who points to x is called its parent. This is the parent of x. So this one is a child of x. Is that okay? So unless you are a root, you will always have exactly one parent. Exactly one parent points at you. Okay? This one has this one as a parent. This one has this one as a parent, and so on and so forth. Is that okay? And then all the one that does not have any children, we call it leaf. Okay? And all the ones that gives you that is not leaf, for instance, this one, this one, this one, this one. Anything else? Okay, so all these four nodes that are not leaves, we call them, they are inside the tree, so we call them internal node. Is that okay? So these are some special names for a tree, and then we can use tree diagram to help us to do counting. But first of all, what? First of all, there are relationships that are among the number of nodes in this graph and the number of edges. So how many nodes are there? How many vertices are there? If you count it, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is it okay? So there are 11 vertices here, 11 nodes here. And how many edges? This is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that okay? So there are 10 edges and then there are 11 nodes. It is always the case that if you have n nodes, then the number of edges must be equal to n minus 1. Why? Why? Let me ask you why. Of course, you can prove this by induction. Okay, you can prove it by induction. Let's say you have a tree with n nodes, and then n is equal to 1, then there's 0 edge, and then you have more nodes, and then probably you do something to reduce the number of nodes. Let's say you pluck out this node together with this edge. Okay, then you will get into a tree that has n minus 1 nodes, and then you know how many edges, and then you add back the edge, and then you get the solution. So you can prove this by induction. But there is a better way to visualize this. Okay, so we call there are n nodes, right? Only one of them is the root. All the others are not root. If it is not root, there is one arrow pointing into it. That's it. So the number of edge must be equal to n minus 1. Do you understand my point? Each node that is not a root, you have a specific edge pointing into it. So the total number of edges must be the number of non-root nodes. So it is n minus 1. Okay, so this is a property about a tree. So a tree is a graph that looks like this. There is a root and then arrows pointing downwards. So each one may have some children, except you are a leaf, then you don't grow. Okay, and how do we use tree diagram to help us to do counting? Let's use an example to explain. So in an example, let us look at the case where you want to count the number of bit strings of length 4 without 1 inside. Okay, so what is a bit string? So a bit string is something like a string that consists of 0 or 1. So 0, 0, 0, 1, 0. This is a bit string. Is that okay? Or 1, 1, 0. This is another bit string. Or 0, 1, 0, 0, 1. This is another bit string. Is that okay? Okay, a bit string of length 4, that simply means that it has only 4 bits. So this is 1, 2, 3, 4, 5. This is a 5-bit string. This is a 3-bit bit string, and this is another 5-bit string. Okay? So we want to count out the number of bit string of length 4 without 1 inside. How many are there? So you can, one way is to do this. So you list out all the possible bit 4 strings. Okay, so 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, blah, 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 blah. You list out 16 of them, and then check out whether each one has 1 inside or not. So this is one method. Okay, this works. Okay, this works. Okay, another way is, let's consider adding the bits 1 by 1. And whenever you see something that is not possible, then we don't care about what will happen. So let's create something that is called the root here. And then if we want to create a 4-bit string, then the first bit can either be 0 or 1. Is that okay? Now if the first bit is 0, then the next bit could be a 0 or a 1. Is that okay? And then the next bit could be a 0 or a 1. Is that okay? And then the next bit here could be a 0. The next bit could be a 0 or a 1. Is that okay? So this one means 0, 0, 0, 0. Okay? This one means 0, 0, 0, 1. Is that okay? And this one means 0, 0, 1. And then the next one could be a 0 or a 1. But if it is a 1, then we should not count it because there are 1 inside. We don't want to have 1 inside. So this is done. If it is 0, 1, then the next one is, it must be a 0. because we want to avoid 1. If 0, 1, 1, then there is already 2 ones that we have. So in that case, this is what we have. So if it starts with the bit 0, there are only 1, 2, 3, 4, 5 possible cases that we can have. Similarly, if we start from 1, then what will happen? So if it is 1, then the next bit could be 0 only. Because if it is a 1, then we should not count it, and we ignore it, then we don't draw it. And then the next bit, you can have 0 or you can have 1. For this 0, you can have 0, you can have 1. For this 1, you should only have 0. Is that okay? So this is it. So if you use, this is a tree. Okay, the tree is, you want to make the decision of the 4 bits one by one. Okay, each time you make a few decisions, only decide the first bit, and then decide the next bit, and so on and so forth. Each leaf corresponds to a particular case that you are interested, and then we want to count how many leaves are there. So there's 1, 2, 3, 4, 5, 6, 7, 8. So there, the number of them is equal to 8 that we have. Okay, so is it good or is it bad? Okay, this is good when the problem that you are working on is very irregular. So that means that you don't have any rule to predict what will happen. So if I change the question into what is the number of bit strings of length 5 without the bit string 110, then maybe this is a difficult problem. It's better to use a tree to help you. Okay, so if the problem looks like irregular and if the problem does not look too large so that you can still draw a tree, then better draw a tree. Okay, but on the other hand, if I'm asking you how many bit strings of length 100 that does not contain the bit pattern 110, then in that case you don't want to draw a tree, because in that case you may encounter up to many leaves, and then it takes a lot of time to finish even your drawing, maybe your whole life. Okay, so it doesn't make sense. So in that case, better try to find out some rules or the relationship among the bit strings of length k with the bit strings of length k minus 1 or whatever. Maybe this will help you to get some general rule to predict what is the next number. Okay, so this is the tree diagram, and then that's it. Okay? Okay, so Wednesday, reminder, we don't have any class. And then on next week, we will continue the discussion on this counting. Okay, thank you.